In lesson 11.3, we're going to examine infinite series. And an infinite series is a series with an infinite number of terms. You'll notice that an infinite series will end with plus and an ellipsis to indicate that there are terms left out. Let's consider the series 1/2 plus 1/4 plus 1/8 plus 1/16 a geometric series. And we're going to represent the sums in a pictorial way. So we're going to represent them as fractions of a whole. So our first partial sum is the first term of the series 1/2. Our second partial sum means that we're going to add to that another term with a value of 1/4. So I'll shade in 1/4 of the square, and our second partial sum is 1/2 plus 1/4, which equals 3/4. The third partial sum, we're going to add an additional term of 1/8. So I'll shade in 1/8, and the third partial sum is 1/2 plus 1/4 plus 1/8, which equals 7/8. And then adding another term, 1/16, the fourth partial sum is 1/2 plus 1/4 plus 1/8 plus 1/16, which is equal to 15/16. Now we can extend that to the fifth partial sum without a whole lot of effort, and we know that the result is going to give us 31/32. The partial sums are approaching a particular value. You notice that they're getting closer and closer to a whole square, and so they are getting closer to a value of 1. This illustrates something which we call convergence. An infinite series converges if its partial sums approach a particular value, in this case 1. The sum of the series is the value that the partial sums are approaching as the number of terms approaches infinity. The nth partial sum of this series above can be given by our nth partial sum formula for a geometric series, which is equal to the first term, 1/2, times 1 minus the ratio, which is also 1/2, raised to the n power, divided by 1 minus 1/2. Now, what I want to concentrate on here is this term right here, 1/2 raised to the n power. If we raise 1/2 to the third power, we get 1/8. If we raise it to the fifth power, we get 1/32. And you'll notice that as we raise it to larger and larger values, the value of the fraction gets smaller and smaller and approaches 0. So with that in mind, if the sum of if the number of terms increases without bound or approaches infinity, the sum of the infinite series is equal to the first term times 1 minus the ratio raised to the nth power, which we said would get close to 0, divided by 1 minus the ratio, which is 1/2. The numerator gives us a value of 1/2, and the denominator is 1 minus 1/2, which is 1/2, and 1/2 divided by 1/2 is 1. So you see we get that infinite sum that we saw illustrated in the picture. So this brings us to the sum of an infinite geometric series. If the geometric series converges, the sum is equal to the first term divided by 1 minus the common ratio. But that's provided that the common ratio falls somewhere between -1 and +1, not including those endpoint values. A geometric series diverges, which means does not have a finite sum if the ratio is either smaller than or equal to -1 or greater than or equal to +1. In other words, not between -1 and +1. All right, let's consider an arithmetic series. 2 plus 5 plus 8 plus 11 with a common difference of 3. The first four partial sums are 2 is the sum of one term. The second partial sum is the sum of two terms. 2 plus 5 is 7. And the third partial sum, we're going to add 8 to that so that we get 15. And then the fourth partial sum, add 11 to that so we get 26. What we'll notice about this sequence of partial sums is that they are not moving toward any particular value. In fact, the sequence of partial sums will just get larger and larger and larger and move toward infinity, which is an idea and not an actual value. What this tells us is that any infinite arithmetic series always diverges. In example 2, we're going to determine if each given series converges or diverges and justify and find the sum of the series if appropriate. So the first thing that we're going to do in A here is we're going to look at the series and decide what kind it is first of all. And it is a geometric series because each term is produced by multiplying the previous term by 1/3. So if it's a geometric series, then it might converge. So some geometric series converge, some do not. What determines whether it converges is the value of r. And our r value here, the number that we multiply by to get from one term to the next, is 1/3. And so since 1/3 is somewhere in between -1 and +1, that means that the series converges. In other words, that ratio is a proper fraction. Since it converges, we're going to find its sum. And the sum of an infinite geometric series is, if it converges, the first term, which is 1, divided by 1 minus the common ratio, which is 1/3. So that sum will be 1 divided by 1 minus 1/3, which is 2/3, and 1 divided by 2/3 is 3/2, or 1.5. In B, if we're trying to decide if the series converges or diverges, first of all, we're going to observe that this is an arithmetic sequence. And an arithmetic series always diverges. So no sum can be found. In C, we have a geometric series, and it's a geometric series, so it might converge. There's the possibility. And that depends upon the value of r. And r, the ratio is -2/3, because 2 times -2/3 is -4/3. -4/3 times -2/3 is +8/9, etc. And that is a value that falls between -1 and +1. So the series converges. Since it converges, we can use the sum formula to find its sum. The sum is equal to the first term divided by 1 minus the common ratio, which is -2/3. Be careful with that. We're subtracting a negative. So that sum is 2 divided by 3/3 plus 2/3, which is 5/3. And 2 divided by 5/3 is the same as 2 times 3/5, which gives us a result of 6/5 for the infinite sum. D illustrates a very unique type of series where each term is the opposite of the one before, which falls into a geometric series. So if it's a geometric series, it might converge. It might not. But our r value is -1. Each term is found by multiplying the previous term by -1. So -1 is not between -1 and +1. It is, in fact, equal to -1, right? And we're not including those endpoint values for convergence. So that means that this series diverges. And if we want to get a better feel for why it diverges, let's find some partial sums. The sum of one term is 2, the first term. The sum of two terms is 2 minus 2, which is 0. The sum of three terms is 2 minus 2 plus 2, which is 2. And the sum of four terms is 2 minus 2 plus 2 minus 2, which is 0. And you'll notice that the partial sums will in fact just bounce between 2 and 0 and not approach a particular value. So that kind of illustrates why this we don't include -1 in the values of R that will give us a convergent geometric series. Your turn to try. Pause the video while you try this one. You should have found that this geometric series does not converge or diverges because their common ratio is 5/2, which is 2.5. That's a number that's bigger than 1. So it's not between -1 and +1. We can illustrate the use of the sum formula here if I mistakenly applied the sum formula, which is not appropriate because this series does not actually have a sum. So if I were to use the sum formula, the sum would be equal to the first term divided by 1 minus the common ratio, which is 5/2. This gives us a sum of 2 divided by 2/2 minus 5/2, which is -3/2. And that gives us a sum of -4/3. And -4/3 is really not a possible sum when you're adding a bunch of positive numbers together. So if we use the sum formula erroneously for a divergent series, it's going to give us a nonsense answer. Pause the video while you try F on your own. For this one, you should have noticed that this is an arithmetic series because our common difference is -1. Therefore, it always diverges. All right, pause the video while you try G. All right, since this one is a geometric series with a common ratio of -2/3, it converges, and we should have found a sum of 3/10. Next, pause the video while you try H on your own. This one is a geometric series with a ratio of 3/10, so the sum can be found, and that sum is 157. In example 3, we're going to write repeating decimals as an infinite series and then use our sum formula to write them as a rational number or the ratio of integers. So 0.9 repeating can be re-expressed as 0.9 plus 0.09 plus 0.009, etc., which is an infinite geometric series with a ratio equal to 0.1. So the sum of this geometric series is equal to the first term in the series, 0.9, divided by 1 minus the ratio, 0.1. So that's 0.9 divided by 0.9, which is equal to 1. So 0.9 repeating is actually equal to the fraction 1/1, or just the whole number 1. In B, we have 2 digits repeating this time. So the first term of this infinite geometric series is 0.024. The second is 0.00024. And the third is 0.0000024. And that continues onward. This particular geometric series, since we have 2 digits repeating, the ratio here is 0.01. So the sum of this infinite geometric series is the first term divided by 1 minus the ratio, 0.01, and that is equal to 0.024 divided by 0.99. Now we want to write this as a ratio of integers, so we're going to have to change this complex fraction to a fraction that's a ratio of whole numbers. So I'm going to multiply by a clever form of 1 in the form of 1,000 over 1,000, because we do want to scoot the decimal point 3 places. So that will give us 24 divided by 990, and we can reduce by a factor of 3. That will give us 8. Sorry, that's a 990 on the bottom, and that'll give us 8 over 330, and we can reduce further by a factor of 2, and that'll give us 4 divided by 165. Your turn to try the next one, 0.0777, etc. Pause the video while you try this one. You should have found a sum of 7/90ths. Now pause the video while you try D. For this last example, you should have found a fractional value of 4/11. In example 4, we're finding the sum of each series in terms of x, and then the x values for which the series has a finite sum or converges. So in A, what we see is an infinite geometric series with a ratio equal to x. And we know that an infinite geometric series converges if the ratio is in between -1 and +1. So since our ratio is x, x has to be in between -1 and +1. In the case that it does converge, the sum of the series will be equal to the first term divided by 1 minus the ratio. So that's what the sum of the series will equal, and that will only happen when x is in between -1 and +1. In B, we have an infinite geometric series with a ratio equal to -x/5. So this series will converge if that ratio, -x/5, is in between -1 and +1. I'm going to multiply all three parts of this inequality by 5. So -5 is less than -x is less than +5. And now multiply all parts by -1. So that was 5 is greater than x is greater than -5, which is still to say that x has to be between -5 and +5. So now we want the sum of our series, and the sum is equal to the first term, which is x/5, divided by 1 minus the ratio, which is -x divided by 5. Now I'm going to change that minus a negative to plus a positive, and nobody likes a complex fraction, so we're going to multiply top and bottom of this fraction by 5. And so multiplying the numerator times 5, we get a sum of x/5 times 5 is x, and then distributing that multiplication by 5 to both terms in the denominator, we get 5 plus x. So the sum of the series is x divided by 5 plus x for x values that are between -5 and +5, which is the interval that we found in when we started looking at the common ratio being between -1 and 1. In C, we have a geometric series with a common ratio of x minus 2/3. So this series will converge if that ratio, x minus 2/3, is between -1 and +1. I'm going to multiply both sides of this inequality by 3. That'll give us -3 is less than x minus 2 is less than 3. And now add 2, and we get -1 is less than x is less than 5. So that's going to be the interval for which we have a convergent series. And the sum of this convergent series is the first term divided by 1 minus the ratio, which is x minus 2 divided by 3. Nobody likes a complex fraction, so we're going to multiply by 3/3 to clear any fractions within the fraction. And doing that multiplication, we get 3x minus 6 on the top of the fraction. On the bottom, we get 3 minus the quantity x minus 2. It's important to realize that there's an understood parentheses around the numerator of that fraction since we have multiple terms there. If we distribute the negative, you get 3 minus x plus 2, or 5 minus x when we simplify. So that's going to be the sum of the series for x between -1 and +5. Your turn to try. Pause the video while you try D. For this one, you should have found that the sum of the series is 2x squared divided by 2 minus x for x between -2 and +2.